Okay, hi guys. Our next topic is one of the biggest topics you're going to encounter in all of trigonometry. This is a topic that as long as you hang around the mathematics, this is going to be in play. This topic is the graphs of the six trigonometric functions. In particular, the graphs of the sine and the cosine functions. We'll deal with the other four as well, but first off, we're going to deal with the sine and cosine functions. So, bear in mind that everything you do with the graphs of the functions, all six trigonometric functions, anytime you're dealing with the graphs of the functions, you must be dealing in radian measure. You can think degrees if you like, but everything you write, everything you do, everything that you put on the picture needs to be in radian measure. It actually would be better for you if you can begin to think in radian measure as well. So, we're going to draw the graphs of, and we'll deal first with the sine function. So the graphs of these two functions, we'll deal with sine first. And just like you did probably back in your basic algebra course, the very first time you graphed a parabola, you made a little grid. You made an x and a little column here, and we're going to have f of x is sine of x. And so we're going to plot a few points on the number line. Here's my number line. My coordinate system. And we're going to plot several points on here and get a feel for what the graph is. All right, so remember from our picture of the basic unit circle that the sine, if we're at a point on the unit circle, sine is the y coordinate. So if I choose x to be, let's say if I choose x to be 0 radians, that corresponds to the point 1, 0, and all we need to do is to pick off the y coordinate. So sine is the y coordinate of the point 1, 0. So sine of 0 is 0. So we have created the point 0, 0 on the graph. That's our first point on the graph of the sine curve. Now let's do the four quadrantal angles here. So suppose we use pi over 2. Pi over 2 corresponds to this quadrantal angle. And the coordinates of that point are 0, 1. Remember, the sine coordinate is the y value on this unit circle. I'm sorry, the sine of the x value is the y coordinate. And so we pick off that. Sine of pi over 2 is 1. So we just found the point pi over 2, 1. We'll deal with this on the picture. Let me just find some points here, and we'll put them on the picture all at one go. Next quadrantal angle is pi. Well, that corresponds to the point -1, 0, the y coordinate of which is 0. So the function value of pi is 0. We just found the point pi, 0. Our next quadrantal angle is 3 pi over 2. 3 pi over 2 in this direction. The coordinates of that point are 0, -1. We select the y coordinate. So at 3 pi over 2, the function value is -1. And I'm going to need to erase my picture a bit. But we can see when we get around to 1 complete revolution, 2 pi, we've got back to exactly the same y coordinate, 0. So if the input of the function is 2 pi, the function value is 0, we have 2 pi, 0. Now, it's not too hard to see that if we continue around the circle the second time we get to this quadrantal angle, this is now 5 pi over 2. But the function value is the same as it was for 1 pi over 2. The y coordinate is still 1. And so as you cycle around this unit circle multiple times, is it clear that these function values repeat themselves in cycle? What we're talking about here is a phenomenon called a periodic function. And we'll talk about that more in just a bit. But the fact that this function repeats itself as you go multiple times around the unit circle causes this function to be what we call a periodic function. We'll talk more about that in just a bit. But now I want to plot these points. Now, it's convenient. Notice the y values are going to go from -1 to small to 1. So there's my -1, and here's +1. But it is convenient on the x-axis not to score this out as 1, 2, 3, 4. It's more convenient to plot this out in multiples of pi. Now, when you draw this, it is important that you draw it at least reasonably accurately to scale. So, if this is 1 unit, see this distance is now 1 unit, pi is slightly more than 3, which means if this is slightly more than 3, then I'm going to call that pi. To a reasonable approximation, that's about 3 units, a little bit more than 3. Well, if that's 1 pi, then this is now 2 pi, and then this is 3 pi, and so on. And in the negative direction, this is negative pi, this is -2 pi, and so on in the negative direction. It is convenient to score off the x-axis, not in terms of 1, 2, 3, and 4, but in terms of pi, 2 pi, 3 pi, multiples of pi. So we've already plotted the point 0, 0. I'm going to use a different color. So this is 0, 0. We now have pi over 2. So if this is pi, I'm going to mark half of that. And then, again, this is just an approximation. It's good enough for our work. This is pi over 2. Is it clear we're going to need the other values of half pi's? So this is 3 pi over 2. This is 5 pi over 2. We would have 7 pi over 2. This is negative pi over 2, -3 pi over 2. So the negative mirrors the positive. At x is pi over 2, the y value is 1. So that's that point, pi over 2, 1. But then at pi, the function value goes back down to 0. At 3 pi over 2, the function value goes to -1. But at 2 pi, the function value comes back up to 0. And as we saw, as we continue around the unit circle, getting coterminal angles, the function values are the same. And so this goes from, it's a cycle, 0, 1, 0, -1, 0. What's next? 1, 0, -1, and that continues all the way out the x-axis. Now, when we talk about the negative values, that corresponds to rotating in a clockwise direction. So this angle is negative pi over 2. That corresponds to the value 0, -1. And so the y-coordinate is -1. And so we see the cycle continues, the pattern continues in the negative direction. This goes from 1 to 0 to -1. It's not hard to convince yourself this comes back to 0, then +1, then 0. And this cycle continues all the way out the x-axis. If you were to plot more and more of these points, you would get a curve within the limits of my badly drawn picture that looks something like this. And so this is the graph of the sine curve. Now, arguing from the picture, is it clear what the domain is? What is the domain? The domain consists of all the x values that are used as input. Well, is it clear that as far as you go out the positive x-axis, the picture exists there? As far as you go out the negative x-axis, the picture exists there. The domain for this function is from -infinity to +infinity. Not a very good infinity. Or if you prefer, all the real numbers. The range, remember the range consists of, one way to think of it is, what part of the y-axis is actually getting used for this picture. Well, is it clear? The minimum, the smallest value achieved is -1. And the largest value achieved is +1. Now, the reason, of course, for that is, as you plot out this unit circle, we are choosing these y coordinates. The largest possible y coordinate is 1. That's why the largest possible function value is 1. The smallest possible function value is -1. As you sweep through this quadrant 3, you score out the value of -1 as the minimum, and that's why the lowest point on this curve is -1. And look at what happens to the y coordinates. The y coordinate is 0, then it goes to 1, then the y coordinates come back down to 0, then the y coordinates go to -1, then the y coordinates go to 0 again, then +1, then 0, then -1, then 0, then +1, then 0. And so that's why this wave continues all the way out as far as you go out the x-axis. Similarly, if you're going in the clockwise direction, you start at 0, then you go to -1, then 0, then +1, then 0, and so on. 0, -1, 0, +1, 0, and so on. So this is the basic structure of the cosine graph. One thing you should be able to do is, with this graph, you should be able to do exactly the same thing that you could do with, say, the basic shape square function. If someone asks you to sketch the basic shape square function, you could draw that. That's not perfect by any means, but that's a reasonable approximation. You should be able to draw a reasonable approximation of the sine curve just like you can draw a reasonable approximation of the basic shape parabola. If you want more detail, you could provide it. If you wanted more detail, you could provide it. But in your mind's eye, you should be able to have a picture of what this graph looks like. Notice that the sine curve passes through the origin. Now, the next piece is this notion of periodic. A function is periodic if there is a finite distance over which the function will repeat itself. Is it clear? If I take this piece of this green picture, cut it out, pick it up, move it over here, and put it back within the limits of my badly drawn picture, it is precisely the same graph. It matches precisely. Take that, lift it, pick it up, move it over here. It would fit precisely. Pick it up, move it over here. It would fit precisely. If you take this distance, there is a finite distance over which the function exactly repeats itself. If that's the case, it is called a periodic function. All 6 of the trigonometric functions have this quality. All 6 of them are periodic functions. All right? Now, every periodic function has a period. Period is a number. It is the minimum distance over which the function repeats itself. Look, if I take from 0 to 4 pi, that's 2 complete cycles. If I take that up and move it over here, it matches precisely. So, same thing if I took from 0 to 6 pi. We'll pick it up, move it over, it would match precisely. But the period is not 4 pi, the period is not 6 pi. The period is the shortest distance for which that process would work. If I tried just to take pi, if I pick this up and move it over, it would not match because it would be going up instead of down. And so the minimum distance over which you can repeat this function is from 0 to 2 pi, which corresponds in the unit circle to 1 complete revolution. For that and a few other reasons, typically when you draw the graph, the sine curve, typically we draw from 0 to 2 pi. You may include the 2 pi or not. Typically when you draw the graph, you do include the endpoint. This is what's called the standard interval. The standard interval is the interval over which you typically draw the graph. So, if you are asked to draw the graph of the sine curve on the standard interval, something like this would be in order. Here's 1, here's -1. When you draw this, it is important to have a reasonable approximation. If this is 1, 2, 3, and a little more, that's pi. So whenever I have students do this, the first thing you mark off is 1 and -1. You mark off the y-axis first. From that, go a little bit more than 3 times as far to get pi. Double that to get 2 pi. Half that is pi over 2. Half that is 3 pi over 2. And then you draw the 5 basic points. The 5 basic points. 0, 1, 0, -1, 0. The 5 basic points. After that, essentially, you're just playing connect the dots and make it look nice. That is one standard interval graph of the sine curve. Typically, when we talk about the sine curve, in fact, this becomes so common, very often students make the mistake of thinking this is the entire picture. It is not the entire picture. The entire picture goes over all of the entire real number line because the domain of this function is all the real numbers. But when you draw only one standard interval, or when you draw one period of the function, typically this is the graph that's drawn. So, it's important to remember a couple things. The basic shape on the standard interval, the domain, you will be asked, and you do need to know the domain. When you're asked about the domain of the sine curve, we're talking about the entire graph, not just the standard interval. When you're asked the domain of the function, you're asked of the entire function. So the domain and range reference the entire picture, not just this little abbreviated piece of it, representative piece of it. The domain is all the real numbers, from -infinity to infinity, or if you prefer, you may use the all real numbers symbol. I will tend to use the all real numbers. For me, it's a little more concise. The range consists of the y-axis values. It is the interval from -1 to 1. Notice the minimum value is -1. That occurs at 3 pi over 2. The maximum value is at 1. That occurs at pi over 2. The minimum value is -1. The maximum value is +1. And those values actually are achieved. And so the range of the function consists of the values from -1 to 1. Notice that's true on both of these pictures. Strictly speaking, I should be getting it from this picture, not this. But the range is the same. The range is from -1 to 1 of the entire graph. This curve never gets above +1, never goes below -1. And the domain is all the real numbers. If you draw the entire curve, it never ends in either direction. So, f of x is equal to sine of x. This is the entire graph. It is periodic. The period, the distance over which it requires to repeat itself, the period is 2 pi. This period of the sine curve is 2 pi. That's the interval over which it repeats itself. Period is 2 pi. Standard interval is 0 to 2 pi. This is not always the same for all 6 functions. It is for sine. The period is 2 pi. The standard interval is 0 to 2 pi. This is the standard interval graph. Just one period of the function. The domain is all the real numbers. The range is from -1 to 1. So that's the description of the basic shape graph of the sine curve.